We start our discussion with Euler's gamma function, which is defined by the following integral representation. We have already encountered that type of integral before, when we were discussing the asymptotic series. Back then, the parameter z was an integer. It was equal to n plus 1, and the integral was as follows. So it's simply gamma of n plus 1. As you remember, we proved by differentiation with respect to parameter that the integral was equal to a simple factorial. We see that our newly introduced gamma function is reduced to a factorial at integer z. Now, the meaning of the initial integral becomes more transparent. For arbitrary z, one can look at the gamma function as a generalization of the concept of the factorial. Not only the gamma function defines factorial for continuous values of z. That much is pretty obvious. There is more to it. We can also ask ourselves about possible meaning of the function for negative z or even complex z. Naturally, to investigate the behavior of the function for negative or even complex z, we need to explore the convergence of the defining integral. Let's look at it more closely. What do we see? First thing, it converges really well at large t due to the presence of the exponential function. On the other hand, there is a power function t to z minus 1. This function doesn't cause trouble for large t. That's because the exponential suppression is stronger than any power of t. But it may potentially create problems for small values of t when z is negative. Indeed, if z is negative, t to z minus 1 simply blows up when t nears the origin. To see things better, let's explore the behavior of the integral at this lower limit. The standard way to do it is to substitute the lower limit 0 with some small but finite number epsilon, and then set epsilon equal to 0 at the end of the calculation. To isolate the potentially problematic region, we split the domain of integration into two parts, from epsilon to 1 and from 1 to plus infinity. We are interested in the first one, which contains epsilon. The second one is safe, because the integrand is regular at the lower limit, which is 1, and at infinity. The dangerous region is near the origin of the first integral. Therefore, we may simplify the integrand expanding all the functions into Taylor series. The exponential is turned into 1, while the power function stays the same. By this way, we have arrived at a simple integral of power function with elementary antiderivative. So we integrate. Here, we assume that z is not equal to 0. Now we see the problematic term. It's epsilon to z. Let's see what is happening at small epsilon. We split z into its real and imaginary components, then split the function itself into the product of two parts. Let's first investigate the modulus of epsilon to z. The modulus of the imaginary exponential is 1, and we are left just with 1 of epsilon to real part of z. And the modulus is finite as long as the real part of z is non-negative. So, is it the end of the story? Not quite, because there is some particular value of z which causes problems. Namely, what if real part of z equals to 0? So z belongs to the imaginary axis. Then epsilon to z doesn't vanish. Its modulus is equal to 1. We are not only interested in the modulus though, but the whole function. And it also has a phase. And this phase contains the dangerous log of epsilon, which blows up when epsilon tends to 0. So, non-zero imaginary z leads to an ill-defined phase. Therefore, we have to exclude imaginary axis from the possible domain of values of parameter z. Now, the condition defining the existence of the integral is real part of z is positive. So the area at which, for the moment, gamma function is defined is the right complex semiplane, excluding the imaginary axis. The question is, can we give some sense to the gamma function with z lying in the left-hand side of the complex plane? As it happens, we can. There is a special procedure in mathematics for this. It is called the analytic continuation. Since we are doing this for the first time, I'll explain this in some more detail. The idea is to rewrite the initial integral in such a way that the new expression doesn't lose its sense for parameter range wider than the one for which the integral was initially defined. Let's see how this works in practice. First, we assume that z lies in the right semiplane, so the integral is well defined. We know that the source of the potential problems is point t is equal to 0. To detach the problematic region, we split the domain into two parts in the spirit of what was done before. The integrand of the second part is regular for any complex z. The integral itself is convergent. Therefore, the second part is regular in the entire complex plane. It defines a so-called entire function of the complex variable. The first part, as before, is the source of singularity at z lying in the left-hand side of the complex plane. Let's transform it into something with more transparent analytical structure. To this end, we expand the exponential function into Taylor series and plug the expansion into the integral. Then the summation and integration can be interchanged. As a result, the integral is turned into an infinite sum of elementary integrals. The antiderivative of each of them is trivial. Now pay attention. At this point, we utilize the condition that z belongs to the right-hand side of the complex plane. This gives us the basis to set the value of antiderivative at the lower limit equal to 0. So each integral yields simple 1 over n plus z term. This way, we transform our first integral into an infinite sum with simple and transparent analytical structure. Let's write down several initial terms of this sum. Here they are. As we see, the sum is defined even for negative z. In fact, it is well defined in the entire complex plane. There are some singular points though. These are -1, -2 and so on, which are just simple poles. So let's see what happened. We obtain this expression minding z restricted to the right complex semiplane. The final result, however, still makes sense in the entire complex plane. The final expression is in fact a meromorphic function of z. Let's remind that the meromorphic function is a function with a countable number of poles in a complex plane. Therefore, we represent the initial gamma function as the sum of the entire and meromorphic function. And this is the essence of analytic continuation. The transformed expression coincides with initial gamma function on the right-hand side of the complex plane. But it also exists in the left-hand side. The resulting function is called an analytically continued gamma function. You see that it looks quite cumbersome. Of course, such a monster is very inconvenient to work with. However, you will learn very soon that this monster is in fact not so ugly at all. It contains a lot of information about the analytic structure of the function. For example, we see that our generalized factorial is turned into something really non-trivial. Now it has poles for negative integer arguments. It also gives us the residue of the function at each pole. As you know, it's just a coefficient in front of 1 over z plus n factor. Here it is. In fact, these poles are of fundamental importance. We'll encounter them many times in what is about to come. We'll see how their very existence makes magic in physics applications. For most cases, it's going to be enough to use the initial very convenient integral representation, and then using the principle of analytic continuation to extend the validity of all the results on the entire complex plane. Now we are ready to discuss elementary properties of the gamma function. The first one is, of course, the factorial relation. Here it is. The proof works by trivial integration by parts, so I'm not going to dwell into too much details here. We start with the integral representation of gamma function and turn the exponential into a derivative. The integrated term vanishes on both limits. On the upper limit due to the exponential term. On the lower limit only when z belongs to the right complex semiplane. Interchanging the derivative and differentiating the power function, we complete the proof. What is extremely important to note here is the range of validity of the proven identity. We use the integral representation. Therefore, the range is automatically reduced to the right complex semiplane. However, we also see that the left-hand side and the right-hand side of the identity are meromorphic functions in the entire complex plane. Indeed, such are both gamma functions and z function. That means that the validity of the identity can be extended on the entire complex plane by the principle of analytic continuation. The second important identity is so-called mirror identity. Here it is. To prove it, we use the integral representation for both gamma functions. This automatically severely reduces its initial range of applicability. Indeed, the argument z of the first function cuts out the right semiplane. Real part of z is positive, while the argument of 1 minus z cuts out area real part of 1 minus z is positive, which is just x is smaller than 1. In the end, the strip of unit width is formed. Now we rewrite the product of two gamma functions first as a repeated integral and then as the double integral over the first quadrant of the TU plane. The very appearance of the double integral gives us a hint which change of variables to introduce. And here it is. So this is our integral and new variables. Now we need to compute the new measure, and for this we need the Jacobian. And here is the detailed expression we need to compute. So let's do it. Next, we need to understand how the mapping TU to PQ transforms the integration domain. For this, we explore the H correspondence. First, we consider the vertical H. It's given by the equation t is equal to 0 and q running from 0 to plus infinity. We plug in these equations into our change and get the parametric equation for the image of this H in PQ plane. Here, the role of the parameter is assumed by u. We see that it is nothing but the vertical H in PQ plane. Good. Next, we find the image of the horizontal H. U is equal to 0 and t is running from 0 to plus infinity. Again, we plug in these equations into the variable change and we get the weird result. The p variable is fine, but the q is a problem. It tends to infinity. Well, the way we approach all that kind of singularities is always the same. Since zero value of parameter u creates a problem, let's change the h of the initial border slightly to avoid unpleasant divergences. To this end, we shift the horizontal h of the initial region upward slightly. Итак, модуль 3, слайд 5. So, here is our shifted region. Let's see if our shift helps to regularize anything. First, we trace the fate of the vertical edge. Now its equation is t is equal to 0 and u running from epsilon to plus infinity. We plug these conditions into our variable change and get the parametric equation for the image. P is equal to u and q is equal to 0. Here u, as before, plays the role of the parameter. So the image is just the same vertical line stretching from epsilon to plus infinity. Now let's compute the image of the most dangerous horizontal edge. It is this edge that just caused us trouble. Its equation is u is equal to epsilon and t is running from 0 to plus infinity. So here is our parametric equation for the image. P is now t plus epsilon, while q is t over epsilon, where t is the parameter. As we see, our shift indeed helped. The infinity disappeared. Now we have just the parametric equation of the straight line. Excluding t, we get the equation for the line. It's p is equal to epsilon q plus epsilon. So it is slightly shifted upward, almost horizontal line with slope epsilon. And the angle between the two edges is almost 90 degrees. So here is finally the image of the region. Now it's obvious that if we put epsilon to 0, the lower line will do coincide with the horizontal axis, and the image becomes the rectangular area, which is nothing but the first quadrant of the PQ plane. So the integration region is in fact unchanged by the integration range is in fact unchanged by the variable's change. This is what makes this change work. Finally, we have all the ingredients to perform the change of variables, the Jacobian and the new region. So let's just do it. So here is our product of two gamma functions. So first, it used to be a double integral. This is our Jacobian, or rather its modulus. And also we'll need the expression for t variable, which is just pq over 1 plus q. So we plug them in, and our product of the gamma function is transformed into, so exponential is turned into e to minus p, obviously. T over u is changed to q to z. dt du is changed to modulus of the Jacobian, which is p over 1 plus q squared times dp dq. And then there is t in the denominator, so it's going to be just pq divided by 1 plus q. So 1 plus q and 1 plus q squared cancel each other, and we are left with a simplified double integral. So it's just e to minus p. P and p cancel each other, so it's q to z minus 1, and dp dq divided by 1 plus q. Alright, so we see that the integrand became separable. It can be split into two parts. The first part is only q dependent, and the second part is p dependent. And this p dependence is trivial, so this integral is simply 1, the second one. So we are left with just simple classical one-dimensional integral. Now we need to compute the final one-dimensional integral. Well, this is just the classical complex analysis integral. I assume you know how to do this. So here is the answer. For those unfortunate who forgot how to do this, or for some reason can't do it, here is a small hint. Consider the following closed contour and make use of the residue theorem. And here is our answer for the product of two gamma functions. Now let's discuss the initial restriction for this proof. As you remember, we used integral representation for gamma functions. This reduced the range of complex variable. This reduced the range of complex variable to the strip of unit width in the complex plane. But the result is the equality between two meromorphic functions, which are well defined in the whole complex plane. Therefore, by the principle of analytical continuation, we can extend the validity of mirror identity to the whole complex plane. Finally, let's briefly mention some frequently used values of gamma functions. It would probably be a good idea to actually memorize them. Okay. First, the gamma function of 1, which is just a trivial exponential integral, which is 1. And then the gamma function of 1/2. So it's a simple integral. And this integral can be taken by the simple change of variables. So let us make this change. T is equal to s squared. So dt is 2s ds, and as a result we have gamma of 1/2 equals the integral from 0 to plus infinity e to minus s squared 2s ds over s. So we have just doubled Gaussian integral. So the integral, as you remember, is equal to square root of pi by 2. And the final result for the gamma function of 1/2 is just square root of pi.